A common morning routine begins with the application of a flavored paste to a synthetic brush, a gesture so routine that the chemical complexity of the substance remains entirely unexamined. Shortly thereafter, a breakfast may be prepared on a pan characterized by a surface so smooth that proteins and carbohydrates slide across it without a single point of adhesion. These two household staples, the toothpaste and the non-stick coating, rely on the presence of the ninth element of the periodic table. This element is fluorine, a substance that functions as the most ferocious chemical predator in the known universe. In its pure elemental state, fluorine is a pale yellow gas that occupies a position of absolute electronic aggression. It is the apex predator of the micro-world, an element defined by an atomic scale hunger so intense that it challenges the fundamental stability of almost every other form of matter.
While it is currently utilized to reinforce the mineral structure of human teeth and to provide the comfort of a low-friction kitchen, its unadulterated form is a nightmare of thermodynamics, capable of igniting substances that are typically considered the very antithesis of fuel. The transformation of this volatile tiger into a domestic servant is a masterpiece of modern engineering, yet the original nature of the element remains a constant threat, held in check only by the most powerful chemical bonds identified by science. This exploration into the hidden mechanics of the elements that build and protect our world is an ongoing investigation into the fabric of reality. Subscribing to the channel and contributing a perspective in the comments ensures that these detailed deconstructions of the physical universe continue to reach a wider audience of curious minds. The physical reality of pure fluorine, F2, is a radical departure from any domestic association. It is a gas that refuses to coexist with the environment. To understand the greed of fluorine on the fingers, one must examine its position on the Pauling scale of electronegativity. On this scale, which measures how strongly an atom attracts electrons, fluorine holds the absolute record with a value of 3.98. In the language of atomic physics, fluorine is the ultimate electron thief. Most atoms possess a nucleus that exerts a pull on its surrounding electrons, but fluorine's nucleus is exceptionally small and carries a powerful positive charge that is barely shielded by its inner electron shell. It possesses 7 electrons in its outermost orbit, leaving a single, high-stakes vacancy. This vacancy drives the atom to act as a subatomic vacuum cleaner, pulling electrons away from any neighbor with such force that it shatters molecular structures instantly. The result of this extreme electronegativity is that fluorine does not merely react, it consumes. If a stream of pure fluorine gas is directed at a glass of H2O, the water does not extinguish the gas. Instead, the water itself bursts into flames. At the atomic level, the fluorine atoms strike the water molecules and physically rip the hydrogen atoms away from the oxygen. This process releases such an immense amount of energy that the oxygen is liberated in the form of ozone and high-temperature gas, creating a flame that burns within the liquid. This is a reversal of standard human intuition, where water is the primary tool for subduing fire. With fluorine, water becomes the fuel. This predatory behavior extends to materials that are usually considered chemically inert. Glass, for instance, is a stable lattice of silicon and oxygen, SiO2, a material so reliable that it is used to store the most aggressive industrial acids. However, to fluorine, glass is merely a collection of reachable targets. The fluorine atoms possess a higher affinity for silicon than oxygen does. When the gas touches a glass pane, it initiates a causal chain of destruction. The fluorine displaces the oxygen, bonding with the silicon to form silicon tetrafluoride, SiF4, which is a gas. To an observer, the solid, transparent glass appears to simply melt or evaporate, turning into an invisible vapor as its structural skeleton is dismantled at the speed of chemistry. Even metals like steel, copper or gold, which define the structural and economic foundations of civilization, are not immune. In an atmosphere of pure fluorine, these metals are oxidized so rapidly that they turn into a fine metallic dust, a fluorinated ash that represents the total surrender of the metal's crystalline integrity. The paradox of fluorine is most striking when one observes a non-stick frying pan. The coating, known as Teflon or polytetrafluoroethylene, PTFE, is composed of long chains of carbon atoms entirely surrounded by a __quote _5 of fluorine atoms. Here, the __quote _6 has been turned inside out. Because the fluorine atoms have already satisfied their hunger by bonding with the carbon, they have reached a state of terminal stability. The bond between carbon and fluorine is the strongest single bond in organic chemistry. It is so powerful that it creates an electronic __quote _7 around the carbon core. To explain this on the fingers, the fluorine atoms are like a suit of armor made of the most aggressive material possible,
which now refuses to let anything else get close.
This shield is what makes the pan __quote _8 when a piece of food or a drop of water sits on a Teflon surface, it cannot find any loose electrons to latch onto. The fluorine atoms are holding their electrons so tightly that they exert almost no attractive force on the outside world. This results in a material with one of the lowest coefficients of friction ever measured. It is an engineering masterpiece where the most reactive element in the universe is used to create a surface that reacts with nothing. However, this stability has a thermal limit. If the pan is heated beyond 500 degrees Fahrenheit, the kinetic energy becomes so great that the carbon-fluorine bonds begin to vibrate and eventually snap. When this happens, the __quote _9 is partially liberated, releasing toxic vapors that serve as a lethal reminder of the element's original predatory nature. The integration of fluorine into human biology via toothpaste represents another localized triumph over the element's aggression. The outer layer of a human tooth is composed of a mineral called hydroxyapatite. While this material is hard, it is vulnerable to the acids produced by bacteria in the mouth. These acids act like molecular saws, slowly dissolving the mineral and creating cavities. When a person uses fluoride-rich toothpaste, they are initiating a process of atomic substitution. The fluoride ions, F-, move into the crystal lattice of the tooth and replace the hydroxyl groups. This transforms the hydroxyapatite into fluorapatite. This substitution is a masterstroke of defensive engineering. Fluorapatite is significantly less soluble in acid than the original mineral. The fluoride ion is smaller and more electronegative than the group it replaces, which means it pulls the surrounding calcium and phosphate atoms closer together, making the entire crystal lattice more compact and rigid. To explain this on the fingers, it is like replacing the wooden beams of a house with reinforced steel. The __quote _10 of the periodic table, which normally destroys everything in its path, has been harnessed to become the ultimate __quote _11 that keeps the human skeleton from dissolving in the presence of biological waste. The industrial management of fluorine requires a level of caution that is unique in the world of manufacturing. Because the gas, _12, its containers, it can only be stored in specialized metal alloys, such as Monel, a mixture of nickel and copper. When fluorine is first introduced into a Monel tank, it reacts with the inner surface to form a thin, transparent layer of metal fluoride. This layer acts as a _13, shielding the rest of the metal from further attack. It is a state of armed neutrality. The fluorine gas is held in place by a microscopic wall of its own making. If that wall is scratched or breached, the metal underneath will immediately ignite, leading to a structural failure and the release of the quote, _14 into the environment. Fluorine is, therefore, a substance of absolute extremes. It is the element that makes our water unburnable and our teeth unbreakable, while remaining a gas that can incinerate a laboratory in a heartbeat. It is a sociopath of the micro-world that has been forced to become a guardian of our health and a facilitator of our comfort. We interact with it every morning and every evening, trusting in the strength of its atomic bonds to keep the beast in its cage. Every time the brush passes over the enamel, or the spatula slides across the pan, we are benefiting from the precise, calculated taming of the most violent force in the periodic table. It is a material that reminds us that in the universe of chemistry, the difference between a tool of survival and a weapon of mass destruction is often nothing more than the way a single electron is shared between atoms. Fluorine remains the apex predator, a shimmering yellow ghost of the stars that has been successfully redirected from destroying our world to reinforcing the very bits of stone we use to chew our food. The distribution of matter throughout the observable universe is governed by a rigorous chemical hierarchy, where the most essential structural elements are produced in vast quantities, while others remain as rare, high-energy leftovers of stellar evolution. Within this cosmic inventory, the ninth element, fluorine, occupies a position of profound scarcity, functioning as a cosmological bottleneck that challenges the standard models of atomic abundance. While neighboring elements on the periodic table, such as oxygen and carbon, are the mass-produced output of nearly every star in the galaxy, fluorine is the result of a specialized and highly precarious nuclear pathway. In the grand ledger of the cosmos, fluorine, F, is an elusive anomaly, a substance whose production is constantly contested by the very nuclear forces that attempt to forge it. To comprehend the origin of a single fluorine atom is to look past the stable, rhythmic fusion of the Sun and into the frantic, high-pressure environments of red giants and the catastrophic terminal spasms of supernovae. The biography of a fluorine atom begins not in the steady burn of a star's youth, but in the final stages of a star's life, specifically within the interior of an asymptotic giant branch, AGB, star. These are stars possessing between 2 and 4 times the mass of the Sun, that have exhausted the hydrogen in their cores and transitioned to burning helium. Within these stellar giants, the process of nucleosynthesis operates like a high-stakes assembly line. In a narrow shell surrounding the carbon-oxygen core, helium nuclei are fused into heavier elements through a sequence of thermal pulses. To explain this on the fingers, the star acts as a cosmic pressure cooker that is periodically __quote _15 _. Every few thousand years, a sudden surge of helium fusion releases a massive pulse of energy and a flood of free neutrons. During these pulses, a specific chain of reactions occurs. Nitrogen-14 atoms, leftovers from previous cycles, capture alpha particles, which are essentially helium nuclei, to transform into oxygen-18. If a stray proton is available in this high-energy environment, the oxygen-18 can capture it to become fluorine-19, the only stable isotope of the element found in nature. However, the engineering of the universe presents a significant obstacle at this stage, the __quote _16 problem. The same environment that creates fluorine is also incredibly efficient at destroying it. If the fluorine atom remains in the hot interior for too long, it will capture another alpha particle and transform into neon, or it will be struck by a neutron and revert to oxygen. For the universe to retain any fluorine at all, the star must employ a mechanism of rapid transportation known as the __quote 17__. Convection currents. Behaving like massive elevators made of plasma, must physically lift the newly forged fluorine from the burning shell to the cooler outer layers of the star before it can be annihilated by further nuclear reactions. This material is then eventually exhaled into the interstellar medium as the star sheds its outer envelope, becoming a planetary nebula. A secondary, even more exotic source of fluorine is found in the heart of a core collapse supernova. When a massive star reaches the end of its life and its core collapses into a neutron star or a black hole, it releases a staggering quantity of neutrinos, subatomic particles that have almost no mass and rarely interact with matter. However, the density of neutrinos during a supernova is so extreme that they become a physical force of nature. This is known as the __18__ or V process. As this wall of neutrinos surges outward through the star's layers, a small fraction of them collide with neon-20 nuclei. The impact is so violent that it physically knocks a proton or a neutron out of the neon atom, shattering its stability. To explain this on the fingers, it is like a massive wind blowing through a forest with such force that it snaps a single specific branch off a tree. When neon-20, 10 protons, loses a proton, it is transformed into fluorine-19, 9 protons. This high-energy shattering is one of the few ways the universe can bypass the standard limitations of fusion to create the 9th element. Despite these violent origins, the amount of fluorine in the cosmos remains remarkably low, approximately 1 part for every 10,000 atoms of carbon. Its presence on a terrestrial planet like Earth is the result of a specific geochemical trap that prevented the element from being lost to space during the formation of the solar system. Approximately 4.6 billion years ago, as the solar nebula collapsed into a rotating disk of gas and dust, the distribution of elements was dictated by the snow line, a thermal boundary where volatile substances could no longer remain as gases. Fluorine is a light, fugitive element, and in its gaseous form as hydrogen fluoride, HF, it would have been easily swept away by the intense radiation and solar wind of the young sun, just as the primordial helium and neon were. The reason Earth retained its fluorine supply is due to the element's greedy chemical nature and its classification as a lithophile, or stone-loving element. During the early molten phase of the planet's formation, fluorine did not remain in the atmosphere. Instead, it sought out a partner that could offer maximum thermodynamic stability: calcium. This was the most important __23__ event in the planet's history. Calcium and fluorine possess a powerful electromagnetic attraction. When they meet, they form an ionic bond of near-unbreakable strength, creating the mineral fluorite, CaF2. This mineral is a dense crystalline solid with a high melting point. To explain the engineering of this on the fingers, the fluorine atoms grabbed onto the calcium atoms to form a ___24__ that was too heavy to be blown away by the solar wind and too stable to be dissolved by the early volcanic heat. As the Earth cooled and the first continents began to stabilize, the fluorine was concentrated in the outer shell of the planet. It occupies the 13th position in the ranking of elements by mass in the Earth's crust, making up approximately 585 parts per million. While this may seem like a small number, it is a staggering concentration compared to the element's rarity in the rest of the galaxy. The Earth has effectively acted as a planetary-scale filter, vacuuming the trace remnants of AGB stars and supernovae and locking them into the crust. Most of this fluorine is found in the form of fluorapatite, a complex mineral that is a primary component of phosphate rocks. The geological history of fluorine is also marked by the movement of superheated H2O through the crust. As hydrothermal fluids, saturated with dissolved minerals, circulate through volcanic fractures at temperatures exceeding 400 degrees Fahrenheit, they carry dissolved fluorine ions. When these fluids reach cooler regions or encounter calcium-rich limestone, the fluorine precipitates out of the solution, crystallizing into the vibrant, translucent cubes of fluorite that miners have sought for centuries. This process of hydrothermal plumbing is what created the concentrated veins of ore that allow for the industrial production of the element today. We are essentially mining the chemical scars of the Earth's internal cooling process to retrieve the __28__ that survived the birth of the sun. The cosmic accident of fluorine is that it exists here only because it found a safe harbor in the mineral kingdom. If fluorine had been less reactive, or if calcium had been less abundant, the Earth's surface would be a fluorine desert. The development of complex biological structures, such as the reinforced enamel of a tooth, would have been physically impossible without this specific cosmic and geological sequence. Life on Earth has evolved to utilize a material that the stars struggle to make and the universe frequently destroys. Furthermore, fluorine plays a critical role in the __29__ and the chemistry of the mantle. Because it lowers the melting point of silicate rocks, the presence of fluorine in the deep crust acts as a localized lubricant for volcanic activity. It facilitates the movement of magma and the distribution of other rare elements, acting as a _30_ that shapes the topography of the planet. In this capacity, fluorine is not just a structural component, but a geological engine, driving the processes that recycle the Earth's surface over millions of years. To look at a crystal of fluorite or a deposit of phosphate rock is to see the final resting place of a high-energy traveler. The fluorine atoms in those stones have remained unchanged since they were first forged in the pulses of a red giant or the neutrino storm of a supernova billions of years ago. They have navigated the vacuum of space, survived the gravitational collapse of a solar nebula, and escaped the solar wind by bonding with the very bricks of the Earth's crust. We are the beneficiaries of a sequence of events so improbable that it can be described as a thermodynamic miracle. The concentration of a rare, fugitive gas into a solid-state resource that we can hold in our hands. Fluorine is the limiting factor that became a structural guarantor, a material that proves the universe is not just a place of mass production, but also a place where the rarest and most volatile fragments can be captured and put to work, providing the hardness and stability required for the evolution of a technological civilization. Every time a fluoride ion is incorporated into a biological or industrial structure, it is the conclusion of a multi-billion-year journey from the edge of stellar destruction to the unyielding reality of the terrestrial crust. The functional landscape of the 21st century is defined by a silent and pervasive reliance on the ninth element, a substance that has transitioned from its role as a lethal laboratory curiosity to become the invisible guardian of our most sophisticated technologies. While the previous historical narratives of fluorine were characterized by the martyrdom of 19th century chemists, the modern hidden engine of the element is defined by its ability to perform high-precision work within the microscopic architecture of the digital brain, the chemical pathways of modern medicine, and the high-energy heart of the nuclear power industry. Fluorine operates as a bodyguard of the modern era, providing a degree of chemical and thermal stability that allows human ingenuity to push the boundaries of what is physically possible. To comprehend the hidden engine of the present is to examine how the most aggressive element in the periodic table was harnessed to manipulate the movement of electrons, stabilize the metabolism of life-saving drugs, and facilitate the enrichment of the fuels that power entire nations. The most critical and least visible application of fluorine in the contemporary world occurs within the high-vacuum cleanrooms where microprocessors are manufactured.
A modern smartphone processor is a masterpiece of subatomic architecture, containing billions of transistors etched into a wafer of hyper-pure silicon. As the industry has moved toward the 5-nanometer and 3-nanometer scales, traditional mechanical and optical tools have become too blunt to carve the necessary pathways.
At this level of miniaturization, the industry relies on a process known as dry etching or plasma etching, where fluorine-based gases such as nitrogen trifluoride, NF3, and sulfur hexafluoride, SF6, serve as the primary chemical scalpels. To understand the engineering necessity of fluorine in this context, one can visualize the surface of a silicon wafer as a massive, solid block of granite that must be carved with surgical precision to create a city of microscopic wires. The process begins by coating the silicon with a protective mask. The wafer is then placed into a vacuum chamber, where the fluorine-containing gas is energized into a plasma state. In this high-energy environment, the gas molecules break apart, releasing independent fluorine atoms that strike the exposed silicon surface at high velocities. Because of fluorine's extreme electronegativity, it does not merely _35 against the silicon. It strikes the silicon atoms and physically rips them away from their neighbors to form silicon tetrafluoride, SiF4. This byproduct is a volatile gas that is immediately sucked away by the vacuum system, leaving behind a perfectly sharp, deep trench in the silicon. This atomic scale _36 is an exercise in extreme chemical selectivity. The fluorine-based plasma is engineered to _37_37_ only the silicon while ignoring the protective masks, allowing for the creation of electrical pathways that are thousands of times thinner than a human hair. Without the aggressive, unyielding hunger of the fluorine atom, the __38_ could never have achieved the density required for artificial intelligence or high-definition mobile computing. Fluorine is the only material in the human inventory capable of dissolving the __39_ of our circuitry with such surgical accuracy, proving that the same __40_ that once dissolved the glass test tubes of the 19th century is now the only tool sharp enough to draw the future of the digital world. The influence of fluorine extends from the circuitry of our machines into the very chemical structure of our biology through the field of modern pharmacology. It is a staggering reality of contemporary medicine that approximately 20% of all commercial drugs and nearly 30% of all new pharmaceutical products contain at least one fluorine atom. This is not because fluorine possesses inherent medicinal properties, but because it functions as the ultimate __41__, altering the fate of a drug once it enters the human body. To understand this on the fingers, a drug molecule is like a complex machine that must reach a specific target in the brain or an organ to perform its task. However, the human body is a highly efficient incinerator.
The liver and the stomach are filled with enzymes designed to identify __42_ molecules and dismantle them using oxidation. Most drug molecules are built on a carbon-hydrogen CH framework, a bond that enzymes find very easy to __43_ through and break apart. By strategically replacing a hydrogen atom with a fluorine atom, a process called fluorination, chemists can create a carbon-fluorine CF bond. This is the strongest single bond in all of organic chemistry. __44_ that is virtually indestructible under biological conditions. To explain the engineering of this on the fingers, It is like replacing a wooden structural beam in a house with a beam made of reinforced titanium that the quote 45 of our metabolism cannot damage. This substitution prevents enzymes from breaking the drug apart, allowing the medication to circulate in the bloodstream for a much longer period and reach its target with a far higher percentage of its original strength. The most famous example of this quote 46 is found in the antidepressant fluoxetine, commonly known as Prozac. The molecule features a quote 47, a cluster of 3 fluorine atoms that provides the metabolic stability required for the drug to cross the blood-brain barrier and regulate the serotonin levels of the nervous system. Without this fluorinated anchor, the drug would be neutralized by the liver within minutes, rendering it useless. This same principle applies to modern anesthetics like sevoflurane and isoflurane. These are fluorinated ethers that provide a level of safety and control that was previously impossible. Unlike the flammable and toxic ethers used in the past, these quote 48 molecules are non-combustible and are handled by the body with extreme predictability, allowing for the precise management of unconsciousness during a 10-hour surgery. We are currently living in a quote 49 of medicine that is propped up by the refusal of the fluorine atom to surrender its bond with carbon, turning the most aggressive gas in the universe into the primary stabilizer of our mental and physical health. Beyond the realms of computing and medicine, fluorine acts as the indispensable quote 50 of the global energy sector, specifically within the complex life cycle of nuclear fuel. The generation of carbon-free electricity on a national scale relies on the enrichment of uranium, a process that would be physically impossible without the intervention of the 9th element. To produce the energy required for a nuclear reactor, engineers must increase the concentration of the uranium-235 isotope from its natural state of less than 1% to approximately 4%. Uranium, in its metallic form, is a heavy, solid, and largely unmanageable material. It cannot be quote 51 by mass in the solid state. To separate the isotopes, the uranium must first be converted into a gas. Fluorine is the only element in nature capable of performing this task with the required efficiency. In an industrial facility, raw uranium is reacted with pure fluorine gas to produce uranium hexafluoride, UF6. To understand the engineering of this molecule on the fingers, fluorine acts as a quote 52 for the heavy uranium. The UF6 molecule is a gas at a very manageable 134 degrees Fahrenheit, which is roughly the temperature of a hot cup of coffee. More importantly, fluorine possesses only one stable isotope in nature, fluorine-19. This means that every UF6 molecule has the exact same amount of fluorine mass, ensuring that any variation in the weight of the gas is entirely due to the uranium atoms themselves. This quote 53 characteristic allows the gas to be pumped into massive high-speed centrifuges. As the canisters spin at speeds exceeding 1,000 rotations per second, the quote 54 molecules containing uranium-235 migrate toward the center, while the quote 55 molecules containing uranium-238 are pushed to the outer walls. This delicate quote 56 dance is the only way humanity has found to concentrate the fuel for our power grids. Fluorine is the courier that carries the heavy weight of the star ash into the air, allowing it to be refined and repurposed. Without the unique ability of fluorine to turn heavy metals into stable, predictable gases,
The era of nuclear energy would have stalled at the beginning, leaving the world dependent on the low energy density of chemical fires and the burning of ancient forests. The __quote_57_ of fluorine is therefore characterized by a shift from the macroscopic to the subatomic. We no longer see the yellow gas, but we live within the consequences of its aggression. It is a material that performs its most important work when it is invisible, confined within the stainless steel chambers of a semiconductor plant, the silver-lined centrifuges of an enrichment facility, or the crystalline structures of our pharmacopoeia. It is the material of the __quote_58_ utilized when the bonds of other elements are too weak or the tools of other sciences are too dull. The paradox of fluorine in the 21st century is that our high-tech comfort, the speed of our data, the longevity of our health, and the stability of our energy is entirely dependent on our ability to maintain a state of __quote_59__. We have learned to use the most reactive substance in existence to create the most inert and stable environments. We use the __quote_60_ to build a world that doesn't burn, doesn't react, and doesn't fail. It is an element that provides the structural and chemical discipline necessary for a high-density civilization to function, acting as the silent regulator of the microscopic and the cosmic alike. Every time we check a notification, take a stabilized medication, or flip a light switch in a city powered by nuclear energy, the ninth element is performing its duty as the most aggressive and reliable partner of human progress. Fluorine has moved from the shadows of the martyrs back to the center of the world, proving that in a civilization built on the movement of energy and the precision of matter, the most powerful thing of all is the element that simply refuses to let go once it has found its target. Without this chemical tiger patrolling the boundaries of our technology, the modern world would be a significantly more fragile, slower, and more dangerous place, succumbing to the entropy that fluorine was born to resist. The human skeleton is often perceived as a temporary biological frame composed of calcium and phosphorus. But for the inhabitants of the 21st century, it is increasingly becoming an indestructible mineral vault of cosmic information. Within the hard tissues of the teeth and the deep architecture of the femur, the ninth element is performing a silent, permanent act of atomic substitution. This process ensures that long after the soft tissues have succumbed to the cycles of decay, and after the carbon has returned to the atmosphere as CO2, the chemical memory of our era will remain etched into the Earth's crust. This enduring legacy is the result of fluorine's absolute affinity for mineral surfaces, a trait that allows a rare stellar gas to transform fragile bone into a stone-like substance capable of weathering the passage of millions of years. This exploration into the deep time archives of our planet is part of a continuing commitment to uncovering the hidden mechanics of existence. Subscribing to the channel and providing a perspective in the comments ensures that these detailed investigations into the substances that define our era continue to reach those who seek a sophisticated understanding of the physical universe. The mechanism of biological preservation through fluorine is governed by the rigorous laws of crystalline symmetry. To understand how this works on the fingers, a living bone or tooth is primarily composed of a mineral called hydroxyapatite. In its natural state, this mineral lattice contains a gap occupied by a hydroxyl group, a combination of oxygen and hydrogen. This group is the structural weak point of the biological frame. It is relatively large and loose, allowing acids and H2O to penetrate the lattice and dismantle the mineral from the inside out. When fluoride ions, F-, are introduced into the system through water or dental care, they perform a targeted subatomic coup. Because the fluorine ion is smaller, more compact,
and carries a much higher electronegative charge than the hydroxyl group it replaces, it slides into the center of the crystalline unit with a higher degree of precision. The result of this substitution is the transformation of hydroxyapatite into fluorapatite, Ca10, PO4, 6, F2.
This is not merely a change in name, but a fundamental upgrade in structural engineering. The fluorine atoms pull the surrounding calcium and phosphate ions closer together, shrinking the volume of the crystal unit and increasing its density. To explain this on the fingers, it is analogous to replacing the wooden floor joists of a building with reinforced steel girders. The resulting structure is not only harder, but is significantly less soluble in H2O. While natural bone mineral begins to dissolve at a pH of 5.5, fluorinated bone can resist dissolution down to a pH of 4.5. This chemical resolve is what allows the teeth of a modern human to resist the corrosive acid rain produced by oral bacteria. But its true significance is revealed only on a geological timescale. When an organism dies and is buried in the earth, it enters the realm of permineralization. This is a process of extreme geological patience, where the elements of the environment gradually infiltrate the biological remains. For most elements, this is a cycle of replacement and loss. However, fluorine acts as a permanent immigrant. As groundwater, which is essentially a dilute mineral soup containing H2O and dissolved salts, flows through the sedimentary layers, the fluoride ions are attracted to the phosphate in the bones. Because fluorapatite is the most thermodynamically stable form of the mineral, the fluorine atoms do not leave. Instead, they accumulate. This creates a phenomenon known as the fluorine clock in archaeology. The longer a bone sits in the earth, the more fluorine it mines from its surroundings. In a million years, the skeleton is no longer a biological artifact. It has become a fluorinated stone, a high-density fossil that carries a higher concentration of the ninth element than any living tissue ever could. The durability of these fluorinated remains ensures that the human species will be among the most legible biographies in the Earth's stratigraphic record. Even if the oceans rise and the continents shift, the white, mineralized fragments of our skeletons will remain in the strata, serving as a permanent chemical autograph. To a future intelligence or a geological process, these remains will not be seen as waste, but as a highly anomalous concentration of a rare cosmic element. In the natural world, fluorine is diffuse and hidden. The presence of billions of high-purity fluorapatite structures in a single sedimentary layer will serve as a glaring signal of a civilization that learned to manipulate the tiger of the periodic table to reinforce its own biology. Beyond the biological frame, the legacy of fluorine is also written in the immortal polymers of the industrial age. The most significant of these is polytetrafluoroethylene, or Teflon.
In the manufacturing of this material, carbon atoms are entirely encased in a dense, protective fur of fluorine atoms. Because the carbon-fluorine bond is the strongest single bond in organic chemistry, it is essentially immune to the standard forces of planetary erosion. To explain this on the fingers, a piece of Teflon-coated technology, or a fluorinated industrial seal, is a molecular vault where the key has been discarded. In a million years, when the iron skeletons of our skyscrapers have long ago turned to orange streaks of rust and the common plastics have been pulverized into microscopic chains, these fluorinated materials will remain. They do not oxidize, they do not dissolve in H2O, and they are not consumed by any known biological enzymes. They will exist as techno-fossils of unprecedented clarity, non-stick surfaces and chemical-resistant valves that will remain as smooth and functional as the day they were produced. These artifacts will provide absolute physical proof of a species that mastered the energy required to create bonds that nature itself could not break.
Fluorine is the only element that allows for the physical archiving of human engineering with such uncompromising permanence, acting as a solid-state record that is immune to the corrosive noise of the environment. The trace in eternity that fluorine provides is not limited to the surface of the Earth, but extends into the deepest geochemical cycles of the planet. As tectonic plates move through the process of subduction, the fluorinated sediments of our cities and our bodies are pulled deep into the Earth's mantle. Here, the fluorine performs its final geological duty as a thermal lubricant. Because fluorine atoms lower the melting point of silicate rocks, the concentration of fluorine in a specific area of the mantle can trigger localized volcanic activity.
The ninth element facilitates the recycling of the Earth's crust, helping to move heat from the interior to the surface. In this capacity, the fluorine that once protected a human tooth in the 21st century may, in 100 million years, be the catalyst for the eruption of a new mountain range. It is a material that transitions from the biological to the volcanic, carrying its high-energy signature through the entire life cycle of the planet. The final and most dramatic chapter of fluorine's role as the biographer of our world is dictated by the inescapable life cycle of the solar system. In approximately 5 billion years, the Sun will exhaust its primary supply of hydrogen fuel and begin the transition into a red giant. As the solar atmosphere expands to engulf the inner planets, the surface temperature of the Earth will climb steadily, eventually exceeding 1,500 degrees Fahrenheit. At this thermal threshold, the oceans will evaporate into the void, and the organic memory of the planet will be erased. However, the mineralized fluorapatite in the Earth's crust and the fluorinated polymers in our technology will remain as the last survivors of the inferno. It is only when the Earth is finally engulfed by the Sun and the temperature exceeds 3,000 degrees Fahrenheit that the tiger will finally be released from its mineral cage. The intense solar heat will provide the kinetic energy required to shatter the indestructible carbon-fluorine bonds and the dense calcium-fluorine lattices. The fluorine atoms will be vaporized, transformed into an atomic gas that will join the solar plasma. To explain this on the fingers, the rare cosmic guest that was forged in the frantic pulses of a dying giant star billions of years ago will finally be returned to the stellar environment. These atoms will carry with them no memory of the dental clinics, the non-stick pans, or the nuclear enrichment plants they once served. They will return to the interstellar medium as pure, unbonded particles, drifting through the vacuum once more. In this cosmic perspective, the history of fluorine is a narrative of profound and honest continuity. It is the element of the absolute barrier, the substance that used its aggressive hunger for electrons to build the most stable and enduring bonds in the universe. We have used this chemical tiger to reinforce our bodies, to shield our technology from radiation, and to bridge the gap between the fragile present and the stone-cold future. Fluorine is the element that reminds us that the quest for permanence is not found in the soft tissues of life, but in the unyielding lattices of the stars.
We have merely borrowed this rare stellar ash for a brief historical second, using its unique structural potential to hold our shape against the entropy of time. When the last human has spoken and the last machine has failed, the fluorine will still be there, waiting in the white bones of our fossils and the smooth surfaces of our polymers. It is the most Chesney biographer because its signature is written in the stability of the atom itself, a permanent yellow thread that runs through the entire fabric of reality. Fluorine is the eternal sentry, a shimmering bridge between the high-energy past of the stars and the cold, stable future of an empty planet, proving that the most influential forces in our world are often those that are the most difficult to tame and the most enduring when finally held in place. Our high-tech civilization is merely a brief resting stop for a material that was born in the heart of a dying giant and is destined to return to it,
carrying the legacy of our ingenuity in the vibration of a single, unyielding bond.